Hello. Good morning, all of you. Okay. So good morning, all of you. I welcome you for this lecture. That is MCA. So I hope you have seen the last lecture or videos what I showed on there. We have started with the chapter number 4, interfacing of the 8051 with the 4 models are there. That is the 4x4 matrix, LCD, stepper motor, ADC, DAC. Okay. So out of that, we have done with the 4x4 matrix and the stepper motor yesterday's lecture. So today we'll go with the LCD and the ADC interfacing with the 8051. Okay. So what was the thing we discussed? Actually, practically we could not able to run that. So today we'll perform the simulation of that. So when the keys press, how it is going to be detected. So let us go with that 4x5 key matrix as I showed shown yesterday. So we are scanning row wise first and then column wise, as rows all connected to the ground level and the columns are at the VCC, means data is going to be 0, 0, 0, 4 times 0, 4 times 1. And when one of the keys pressed, what happens? That particular column goes to the 0, means that pin D of the port 2 going to be 0. That time I can say that at the first row, second column key is pressed. So this port goes to the 0, like that. So I shown the next slide, I'll show it here. You can see here. So when the 1 key is pressed, by default column is 0. So from the D0 to the D1 pin goes to the 0, means we have pressed this. Okay, so continuously we are scanning the each row and the columns to sense the which key is pressed, and appropriately we are displaying on that. And I'm comparing it, masking this data with the 4 times 0, 4 times 1. So I can say that there is a change in the bit number 2. That's why the D0, D1 bit of the port 2 is going to be 0. So I can say that at the row 0, the button is pressed, and this data will I'm sending and it will display on the port 0. This code was seen. So I will show it here by demonstration of that. I will add that file. So 4x4 matrix. Here on build. So for 5 will know here is that you can say. But the thing is that actually we need extra hardware to see that code. Okay. So when the particular key is pressed for row number 1 and the values are taken different way. So we need 0, 1, 2, 3, like that values. Means when that as I discussed, but key is pressed, that time it will show the this button is pressed. Okay, means one value will be displayed on that. So just debug it and just take the peripherals. Port 0 also I need, and port 1 is there by default. Mention that. So by default, port 0 is connected to the columns. Okay, all the rows, 4 rows. So it will be by default 0, 0. So I am taking the port 1 as a input, and the port is going to be output. And by default, values will be 0. So just run it. You can see that. Okay, but when I am pressing the key, where the keyboard is connected to the columns, all the columns are connected to the these 4 bits. So when I'm pressing the one of the bit, the data value is going to be changing, and that data value you can see is going from the A and A to the port 0. Okay, but it is not showing here because we don't have the hardware values. Okay, so we need the hardware, then I can say that appropriate key is going to be pressed by like that. This was the actually remembering the simulation of that. Stop it. Minimize Okay. So then we'll go with the next interfacing. Actually, we need the next interfacing with the LCD. Okay. So 16 by 2 LCD can be interfaced with the 8051 controller. And thing is very, very easy. So what is meaning of 16 by 2? We have the 16 characters in the one row and the two, sorry, 16 character in one row. So like this, we have the two rows, row 1 and row 2. So each line has the 16 characters on the display. Okay. So based on the pins, if you observe that, I will take this LCD and copy here on the paint window. So based on the pins, what is important pins are there that is connected to the ground or VCC. So out of that, we have the D0 to the D7 pins, total 8 data pins are there. Out of that, I'm using so D0 to D7 are the data pins used for sending the data values messages. Okay, remaining 8 pins, these are the 8 pins, total 16 pins are there. Remaining 8 pins are called as the control pins, including VCC ground and backlight control. Okay, out of that, we need the read write pin and RS select and enable. Okay, so these three pins are important when you interface the LCD along with the 8051. Okay, so by default, this RW bar is grounded, means it is connected to the logic 0, meaning that I'm writing the data always on the LCD. So I'm writing the data on the LCD. So meaning is that the read write pin, it is actually bar is there, so it is grounded. Means it operates in the writing mode. I'm not reading. If it is connected to VCC, it is reading is there. But I'm sending the data from the 8051 toward the LCD. The message is displaying on that. So I can say welcome. So actually all the capital letters are there. It's welcome. This message is displayed and I can check by a simulation also how it will be displayed. Okay, so that's why this pin is going to be grounded, means it is we're writing the data on the LCD. Okay, second pin is RS select. So based on the value of RS select, it is 0, RS select is 0, then it operates in the command mode. So LCD operates in the command mode. And if RS is equal to 1, that means it operates in the data mode. Command means what? So we need to bring the cursor at the first row at which character, all these things. So various commands can be used to operate the LCD properly. That means we need to set the RS pin 0. Then I can say that it operates in the command mode. So bringing the cursor on the front row, starting from the first line, starting from the second line, starting at the which character. So all these initialization we can do in the command mode of the LCD operation. Okay, in the data mode, if RS pin is going to be connected to the 1, so this 2.6 some pin is connected to RS pin. Okay, this pin. So what is the message is there? It will be sent on the LCD. When by enabling the pin. So we need to send active high to low signal on the LCD. That what is the data available on these pins will be transferred character by character. So I can say W. W has the value something. We talk about ASCII value of the W is going to be 87. Okay, it's a decimal value. So if you talk about this 57H, this value means 0, 1, 0, 1, 0, 1, 1, 1. So this data value 57 character by character transfer from the LCD when the enable pin is going to be going from low to high pulse. Okay, so like this LCD operates and we have the various commands for that. So meaning of 16 by 2 LCD is what? We have only 2 rows, and in that 2 rows we have the 16 characters. So each character occupy like this. So I can say starting from the 0, I can say 1, 2, 3, dot, 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 I'll put here. So it's a 16, 15, and 14. So in one row, maximum 16 characters will be occupied, and the second message will be on the second row. That time I need again use to have the some commands to bring the cursor at this position to write down the data here. Okay. Then remaining pin we have the ground, VCC, and the backlight control. All these pins are there. So total 16 pins used for that. So out of this data pins D0 to D7, I'm using the LCD in the mode 0. So mode 0, I need only D0 to D3 pins or D4 to D7 pins. So it operates in the 4-bit mode only. It's operation in the 4-bit data mode. It is mode 0 of the LCD command operation. Okay, so this thing we'll see it is in the slide. Let's say that. So as I said that I'm operating the LCD in the 4-bit or the 8-bit. So when I'm operating the LCD in the 4-bit, I need only this 4 to D7 pins, upper MSB pins I need only. With 8-bit interface, total D0 to D7 pins I require to use. Okay, and control pins, RS, read write, and the enable pin. It's not enable actually, it's enable pin to be used high to low signal. Okay, that will interface. So this shows the interfacing diagram of that. So either port 1, I'm connecting this port. So P1.0 to the P1.4, this D4 to D7 pins are connecting. So let's go with that code. So these are the commands I need to use to set the bring the cursor. If I use the command I'm sending move a comma hash 01, meaning is that clear the screen. What was the message on their garbage value? It will be clear all the screen by sending the 01 data on the LCD. When I operate in the command mode, send this command, sending a 0 hash data on the port. 02 will return the home. 4 decrement the cursor, shift cursor left. I'm shifting forward or backward. So I need to use the this command code 4 and the 6 for sending right, left and the right towards that. Then 5-7 shift display right, shift display left. 5-7 we used. 8 if when I use the 08 on the LCD I'm sending, that time display will be off, cursor will be off. All the things will be off automatically. By sending A, I can make the display on, cursor off. Okay. By sending E, I can use. By sending F, I can make the display on, cursor blinking. So you might observe that LCD screen is going to be blinking that way. Okay. So out of that, I need the 01, 02, then 38, use 2 by line, 5x7 matrix dot. Okay. So what is the meaning of 5x7 matrix? I'll tell that also. These commands 80 also I need to force cursor to the being at the first line, 80 commands, 0C also I'm using. Okay. So this command I'm using for in the command mode to set the cursor position at 1 and use the to display the character, what is the exactly size of that pitch. Okay, just wait, I'll show that part here. Okay, so I was discussing about the 5x7. What is the meaning of the 5x7? So to display one character, I have the in simple that one square. I have the 5 dots like this and 7 dots like this. It forms the 5 by 7 means 5 4 35. 35 pixels will be there like this. Okay, like that. In that pixels, my letter, for example, I can say W. So W will be formed like this by connecting the each pixel of that particularly. That meaning it is called as a vertical pitch like this and a horizontal pitch. So that vertical pitch and the horizontal pitch will form the 5 by 7 dot matrix. And in that dot matrix, in one square, my character will be displayed. Okay, so if you observe that sometimes on LCD like this, it is blinking will be there. That will cursor position. Okay, that I'll show it here only. So I'm using 38 means what? 5 by 7 matrix of that to display the one character. So go to the So this is the flowchart. When I'm using the command mode, what to do? Start, push the data on the port, clear RS. So see, clear RS, clear RW means I'm writing RW bar is there. I'm writing on LCD and CS bar 0 means I'm operating in the command mode. Then set enable. So pin enable going to be set to high. Add delay. Some delay will be added to set the cursor all here and all that. Clear enable. So high to low pulse will be sending on that, and that command will be displayed. And as per the command I'm sending 0, 1, 38, all these things, the data will be cleared out, cursor will be take the action and LCD will be clearing the data. Okay, so this is in the command mode operation. So clear screen, all these things, bringing cursor at the first position. So these commands I am transferring in the command mode. Now, when I come to data mode exactly, RS pin must be to be set. So RS equal to 1, it operates in the data mode, and the clear RW means I'm writing the data on that port. So what is the message I'm sending here? Welcome, or what is the today's Monday and all these things. Okay, so that time this message, what is the data will be latched as I showed that character by character, the ASCII value of that. Then set enable. That again I have to use the enable pin to be sitting high as I showed here. The enable pin be going high to low will be latch the data on the LCD from the port, which port is connected for that. Okay, then add some delay and then after delay clear the pin. So data will be displayed on the LCD like this message you are getting here. So see the code, very easy code is there. It's not that much difficult. I will just little bit zoom it out. As I am starting with the 00 address, then I'm defining the RS pin connecting at the port 3.2, meaning is that RS pin is at the 3.2. So send when I clearing P RS, so here after P 3.2 is called as RS pin now. So RS RW read write pin at P 3.1 and the enable pin at the P 3.0. So by setting pin this P 3.2 is equal to 0, it operates in the LCD operates in the command mode. If P 3.2 is equal to 1, it is in the data mode. And by default, P 3.1 is going to be grounded, means it's 0, 0. So that will write the data on the LCD. Okay, then E, I am sending high to low pulse, set by first set, delay add kara ani, then clear this enable pin. So it will be keeping high to low signal. Okay, then use some commands that I use the first command 38, meaning is that I'm using the two line operation, 16 by 2 operation and the 5 by 7 matrix. If you observe the 38 command here, see 38 means what? Two lines, that is the two rows of 16 character and each character occupying in the 5 by 7 matrix. Okay. Then I'm calling the a call command. What is the command we written? We'll see that part also. Then I have the second command move a comma 0e. So bring LCD is on, cursor is on, meaning of that command. Then again a called command. What is the command in return? What is the command I'm writing? I'm writing that RS pin 0, RS pin equal to 0, right bar, and the enable signal E is equal to high, and then E is equal to low. That will come in the command configuration and sending that on the that port, P1 port. Then move a comma 01. So that means clear the LCD, all what is written on the LCD, it will be clear all these things. Then a call command. Then move a comma 06, shift the cursor to the right. That is meaning of that. A call command then again. Then move a comma 81, cursor line 1, position 1. So it will come at the first row, first character. Meaning is here. It come at this moment. First row, first character. By setting the 81 on the command mode operation. Okay. Then a call command again. Then After that, I'm sending the my data. Okay, so move a comma hash w means what? Display the letter w ASCII value. Now, how to check now in the simulation? If you observe, I'll show the ASCII table. The ASCII character or w is going to be the value is 87, and that 87 is the decimal will be 57 in the hex value. So that in the port 1 will get the value 57 means I'm sending the character w. Then a call data display. So what is in the configuration? We'll see in that when we'll call the a call data. In the data mode, what I require to do? RS pin must be set to 1, RW to the 0, and then enable high to low. Then second character, what is the message will be there? We have to use every time this. So move a comma E. So E value will be 65 in the decimal. Oh, sorry, A value is 65 actually, but E ASCII value is going to be 69. So I can say that 65 plus 40 equal A, B, C, D, E. 5 will be added in that. Okay, so A will be 65. E means after that adding the 4, in that we'll get the 69 value. The 69 in the decimal, 45 in the hex. So I can get the 45 in the port 1 data value. Then a call data display. Then move a comma hash L, the second character I'm transferring on the LCD. That is meaning of, and the value will be 74D. Nothing but 4C in the hexadecimal values. Okay. Then again I'm calling a call delay. So the display will be sending this letter one by one, character. So total message is a welcome. That message I'm sending on the LCD, and after each character I'm calling the delay for that. And the last we have the, I'm keeping this in the loop, a jump here. So here will come here only. So this will be unless this all characters will not transfer to LCD. This is in the loop. Now we are remaining with the two subroutines, a call command and a call data. Let's see that commands. So when the a call command will be called from this point after sending the data command 30 value, what exactly happens in that? So what is that contents are coming on the A? I'm transferring this data on port 2. Okay, by transferring the data on port 2, the data will be goes, and what value coming in that? A30 08 value is coming on that. So in that also I'm clearing the RS pin, means I am operating in the command mode. RS equal to 0 for command operation. Clearing R, writing the data on that. Then setting the enable pin, means keeping high level signal. Then for short duration, a call delay and clear E, means what is the command will be there coming. It transfers on the LCD, and as per that command operation, the cursor position LCD on all this thing will be operated. Okay, so after this return means will go comes to the command line here. Again I'm sending the next character. So like this, when the a call command will be called, that subroutine will be executed. Similar way, when I'm transferring the data value a comma hash w, that time I'm calling the data subroutine. So in the data again same, on the port 2 I'm sending the data. What is the data coming welcome message? And I need to control base set B RS1 RS equal to 1, means LCD operating the data mode. Then after setting that again clear RW. RW is what? RW equal to 0 means I'm writing the data on the LCD. Then again I need to latch the data by setting high to low pulse, set B E, a call delay, and then clear E. Again return. So after each character sending means I'm sending W, then a call data means all this data code will be executed. It comes back, then second character E is going to be transferred, then a call data will be executed. And when it comes from a call delay, the delay some short counter will be executed and will be 0, and it comes back here. Okay, so like this, the character by character message I am transmitting. So I have the code of that. We'll see the simulation of that. LCD, I have saved a code. Just build it. And you can see the same code I return, sending the message welcome. And I'm checking on the port 2. So because I'm sending the data on the port 2, so use the port 2 operation. So out of that, I need only port 2. Okay, other ports I don't want. So can say that character per character I can check it. So I don't want also logic analyzer. I'll cut it. Step over, I can run the code. See, After that point, PC is going to be a call command. So it will go to a definitely a call command, and the data will be displayed on the port to 38. So it is operated in the command mode. See, I'm giving the data 38. Then 0E, 01, 06, 81. So after 81, the message will be coming. It come out of that command mode. It goes to the data mode operation. So you can see now the W value is having 87 in the ASCII value decimal, but 57 in the ASCII. So, okay, hexadecimal. So that 57 will be displayed on the port 2, means I am sending the character W. So after W, what was the value I used? 5745 4C. So this data value is coming on the port, means I'm sending the letter WEL. So like this, you can calculate for the other thing also. C45, then 4C. So WEL is transferred on the LCD, is displayed character by character. Similarly, it goes for the next. Okay, and when it's over, you can make it run. So all the messages display on the LCD. So it's for writing LCD code is very easy. Must have the understood the logic for that. Okay, what character I need to send and how to operate in the command mode, in the data mode. So logic, I'll repeat one more time. So to bring the LCD, I will clear this part. I also written here only. So to operate in the command mode LCD, first thing is RS must be 0, then read write pin is equal to 0. So I'm connecting these pins P RS P3.2, P3.1, and P enable is 0. And read write by default it is grounded. Don't note any of that. Okay, and but it is connected to set 0 or not. P3.1, this pin. And then enable should be goes high and then low after some delay. This is I am operating in that, and in that command operation I am using that, and this is port 2 point, that values are used for the connecting the 4 lines of the data D4 to D7. Okay. And to operate in the data mode, just changes that other things will be same. That's RS is equal to 1, read write bar is equal to 0, then same enable equal to pin high, then delay call, and then make the 0. That time data will be latch, and I'm getting the message welcome. So character by character. Sure. Let's go with the next. So I displayed here also what is the value of the capital A letters and W. You can see it is 7 in the decimal, but its ASCII value will be, hexadecimal value will be 57. So next part is that interfacing of ADC with the 8051. Let's go with that. So ADC interfacing with the 8051. So in 8051, we don't have the on-chip ADC. We need to interface externally. Okay, so 0808, the IC name for that. So it has 8 input channels. Okay, so data level is going to be digital. The meaning of ADC is what? Convert the analog signal into digital. What is analog? So on the one of the channel, input channel number 1, I'm connecting analog signal of the 5 volt. Okay, so this 5 volt can be converted into the digital data. Okay, so by using the potentiometer, I can vary from 0 to 5 volt. So based on the size of ADC, now it is 8-bit ADC. We have the resolution of that. On how to find the resolution? we have the formula for that. V reference voltage, what is used, divided by 2 raised to n minus 1. So reference voltage means what? What is the supply voltage I'm connecting maximum here? That is going to be always 5 volt divided by what is the size of ADC? N is going to be 8 minus 1. This gives 5 by 2 raised to 8 will be 256 minus 1, which gives the 255. So when we do this, I'm getting the 19.88 millivolt is the resolution. Okay, so it's nearly equal to 20 millivolt. Meaning is that when I'm giving the voltage of this 1 volt, 2 volt appropriately, what is the digital data I'm getting here, that will be converted. Means, for example, if I write D0 to IN1, so what is the input data coming on the IN1, and I have the output data D0 to D7. Okay, so I'll write from MSB to the LSB. D7, D6, D5, D4, D3, D2, D1, and D0. So this is my digital data. So when I'm giving the first 0 volt, by default data on the converter will be 00 8-bit data. So it gives the 8 value output. Okay. So for input 0 volt, I'm getting this data. So when I'm getting the first variation, means in the multiple of the 20 millivolt, for the next value of this 20 millivolt conversion, I'm getting data 00. First data will be 1. Then it multiple of the second. 20 plus 20 will be 40 millivolt. It will give the this bit 000 0 0 0 1 0. Here 0. Okay. Then 60 millivolt. Then 0 0 3 value will be coming. 1 1. So like this, it goes on the continuation up to maximum what? 5 millivolt. Means it's a 5000 millivolt. Means it is going to be 5 volt. So when exactly 5000 millivolt come, so all the bits of this ADC output will be high. So it's swing between the 00 to the 8 times of 1. So this data will be available. Means as I'm varying my input voltage from 0 to the 5 volt, this so internally this ADC will be sense these voltage levels as input 20 millivolt 40 multiple of that. So when it comes, if I giving the I can say 2 voltage input here DC. So what is corresponding conversion of the data available digital data? So you can go like this, conversion multiple of that. Okay. So 20 millivolt 2 will be 440 millivolt. So to get 2 volt exactly, I need to go multiple of that. So exactly 2 volt will not get. It's a multiple of 20 means 60, 80, 100. Okay, 100, 120, 50 times. Then will come out the 2 volt output of that. Okay. So needs means what? I have to go for the 50 lookup table. Then I'll get the value of 2 volt. And the corresponding data will be getting that. Means as I'm varying their analog voltage from 0 to 5 volt, the data value is going to be changing here. Okay, and like this, it converts the input analog signal into appropriate digital output. Now, for example, I'll tell if I given 0.1 volt, 0.1 volt means what? 100 millivolt. So what will the data for 100 millivolt? Now it's a 60. I'm getting the 3 value. For 80, 4. And for the 100 millivolt, I'm getting the 5 value. 5 means what? I'll use the different color to show it here. This will be 0, 0. I'm talking for 100 millivolt. 0, 0, 0. This will be 0. This will be 0. This is 0, 1, 0, 1. So this data will be coming for the 0.1 volt input is there, then data available for digital will be so 8-bit data 0000101 like that. And when it reaches to maximum value 5 volt, the data will be all ones. Okay, so like this, it changes ADC, what data is coming on that. Let's go with the diagram in that. See, I mentioned here it has the 8-bit ADC, that is 0808, and 08089 is the ADC, and 000 will be DAC. Okay, so it's a variable available 8-bit, 10-bit, 12-bit, 16-bit ADC sizes there. As number of bits increases, so resolution value will be decreasing. Means I can measure the minimum voltage also. Maximum ADC can be when we have the analog sensors and we have to send the analog data. That time ADC must be used. When we talk about higher microprocessors, the controllers, for example, we have the Arduino also, PIC also, embedded processors. It has on-chip ADC and the DAC of size 10-bit. Okay, so I have shown here for 8-bit conversion to restore 56. So 5 volt divided by that, it will give the 19.88, which correspond to nearly about 20 millivolt is the resolution value of that. Okay, then for 10 millivolt to restore 10 means 1024. So 5 volt by 1024 will give the 4.88 millivolt, means nearly 5 millivolt. So you can say this increasing the 2-bit will give the from 20 millivolt to the 5 millivolt is the resolution value. This is diagram I have shown. Along with this also I need some selection lines. Which channel I am using for that? As it is 8 channels, I am using the 3 select lines. So by creating appropriate 0, 1, if it, all the pins will be 0, 0, I am using the IN0 pin input channel. If it's 001, that time I am using the IN1 channel. Okay, so like this, I have to set this P2.2, P2.1, 2.0 such that I can take the input from the one of the signal. And other pins for D0 to D7, data pins port 1 is connected, and control pins read in the right bar. So I'm reading the data, I'm not writing also here. So read by only pin I'm using, that is connected to the OE bar of the ADC. So pin description is given here, that is not important. Okay, so to write the code, first we have to initialize timing diagram for that. So the pin ALE should be always go high to low, sorry, low to high signal should be sent down the ALE pin. Then when the input signals are applied to ADC, I need to start the conversion. So SOC pin, meaning is that start of the conversion. Also it is going to be low to high pulse can be sent after the ALE low to high goes signal. Then after sending the just we have to wait that the conversion is completed or not by looking to the pin EOC, that is end of the conversion. And this is high to low pulse, means when the pin EOC goes low, I can say that ADC has converted the what is input signal analog applied into the digital format. Okay, once this data converted over takes place, I'm sending the signal low to high on the Y bar signal, means what is the data available on the ADC channel output D0 to 7 transport to the port, that is the port 1. So this is the initialization condition is there. Let's go with the code now. So starting with the over the 00 code, then I'm defining these 3 pins, that is control ALE bit 2.4 have connected, SOC pin 2.6 and then EOC pin 2.5 and OE bar 2.7. Along with this, I need the address of the channel to select the which channel input channel I'm using for that. So P2.0, 2.1, 2.3 ABC pins I'm using for that. Then starting initially I am keeping ALE 0, means low signal is there. After that I'm making high. SOC also clear, say to be EOC. So EOC must be high level signal. If you observe here on the this graph, ALE low, SOC low, but EOC should be high level signal. Okay, that I had done at this moment, and clear OE also low signal. Then as I'm taking the sensing the ADC output on the port 1, so I need to use configure the port 1 as a input port. And how to configure this? By sending the data high level on that. That's why move P1 comma hash 0FF will be acting the port 1 as a input port. So sends the data from the ADC and it will taken into the P1 port. This is starting initialization of the code. Then actually code starts from that. So clear C pin set B means it's a 0, 1, 0. So second channel I'm using, meaning is that. Okay. So by selecting the address, simple like a multiplexer. Okay, 0, 1, 0. The output input I'm selecting is 1. Then to make the startup conversion, set B LE. So what was the low signal was there? I'm setting to the high level and I'm starting the taking the data input voltage analog. Set B SOC. So LE is high level, SOC also high level. And after that, just making high to low pulse, clear ALE, clear SOC. So then what is the data input available on the pin number here? IN1 is taken inside for the conversion as per resolution multiplied that value input voltage and data will be available here. Now need to check that it is over or not by sensing the pin EOC. So JB EOC here means wait JBC will go to the high. Now it's high, then if it is go low from high to low means conversion is going to be over. So JNB EOC here. Check that EOC pin is low. If it is low, it come out of the loop. Set BOE means data available will be transferred from this OE pin sending to the port here. Data is going to be reading from the D channel, D0 to D7 pins. And once it is or set BOE over, move A comma P1. So from the port 1, what is data is coming, digital data I'm sending to the accumulator. Then clear OE, data is read over A call convert. Then A call display and A call delay. So this data will be displayed on the LCD. This is ADC code is there for that. Then next will be we have the DAC. If I'm connecting here ADC input analog signal that will be converted to the digital. Then at the output stage, I need to convert this digital data coming into the again analog format. That's why I need to interface the DAC 0 with the microcontroller. Okay, so depends upon the data values given on this 8-bit data, digital data, appropriately by current form, it convert into the analog signals. It may be the sine wave or the triangular wave. So I'm looking forward to show it here, the triangular wave generation by using the DAC. Okay, so this is simple code we have to use it. So I'll copy this code. So this is DAC interfacing with the 8051 to generate triangular wave. Okay, and generation of triangular is very easy. What is triangular wave? So it starts from the 0, go to the FF. Okay, and then come to 0. But actually, it is not linear. It has very small steps like this. If you zoom out, you can see on the DSO, I'm getting the wave like this. If you see the PCM output, the step size is going to increase, decrease in case of DM and the ADM like this. So what is logic? Take the data maximum. So it's from the 0 to the FF. So take the data 0 or IFF. So if I am taking the 0 increment, if taking the data FF decrement, this is logic I'm using for that. Okay. So initially, what is the data I'm using? In the accumulator, I'm sending the 0 value and it starts incrementing to the FF. Take the counter value, one of the register FF, and keep in the loop. So it will start incrementing step by step, and I'm getting the triangular wave. So once it reaches to the maximum value, next task is what? Start decrementing. Again for the FF to the 0. It will come to 0. And this thing I have to repeat for multiple times. So keep in the again loop. So see that code is very easy. So starting with the over the 0. Okay, then start move R4 comma hash for FF, meaning is that I'm taking the maximum value FF and I'm using this as a counter to decrement it. So then I'm making the clear A. So A will be equal to 0. That is the initial point of my triangular wave. Then sending this accumulator value to the port. So move P1 comma A. So what is the A value is going in the port? So port 0, port 1 will be at the 0 position. Then INCA. So what was 0? It will be 1. then 2, 3, like that. It is how many times? 255 times will be in the loop. So this value come at 55 times, means it is a FF. Once accumulator reaches to the FF value, it comes out of the loop, means R4 becomes 0, it comes out of the loop. Then I'm taking other register R5, I'm taking the same counter value FF, and I'm sending this value into again port 1, but now as it is reached to the maximum P1 port, I'm decrementing that. So decrement A. So it starts from decrementing up to which value? 0, 0. Means from 255 to the 0, it goes down. So decrement A 255 times, in that is in the loop, unless R5 will be 0. This is in the loop. And all these two loops I'm keeping in the one more loop, that will be edge jump start. So after one rising and the falling edge over, then next I'll get the like this. So this will be in multiple times. Let's understand that. I will I have the code in the, I will do the simulation. So ADC simulation is quite difficult. We need hardware, but DAC we can perform here. So DAC.asm. No error. This is the DAC code. So what things were written? Same. Taking the R4 with the FF data, and then clearing the accumulator, and then CM value sending and increment A. This is for the 255 times. So from 0 to FF, A value will increased. So it will form the rising edge. And once it is over, I'm decrementing the accumulator from 255 to the 0, means I'm getting the falling edge. Let's debug it in go for running. So I need only port 1, and I need again so port 1 is there by default on the logic analyzer. So I'll get the wave here. So I will change the color of that also. Just run it. See that. So I'm getting the square wave. Not square wave, it's a triangular wave, rising and the falling. So it's from 0 to the maximum FF only. Then it is decrementing. See. But it has some small steps. If I am able to stop it, I can hold the data. I need analog only. See, if I zoom out, you can see small steps in that. You can see. So this counter will be from starting from the 0, 0. It tries incremented accumulator to the which value? 55 to 55. That is FF. And after that, I'm starting decrementing the accumulator from FF to the 0. So that will form the rising and the falling edge. Then this I'm keeping in the loop. So like this, I'm getting the triangular wave on the DAC output. That is analog voltage. So like this, we can now I starting from the 0. We can start from the higher to lower. And I can generate a sawtooth wave also. So just we have to change the logic of that. Like this, just starting from the 0 to the FF, the first code will be same, and directly coming to the 0 here. So it will generate the sawtooth wave. In the stepper motor code we have seen yesterday only, but the C program was remaining. Let's we'll perform that also. Stepper motor C. So missing was we have to add the hash include std.io because standard input output I define the variables. It is why I int all this thing. So I need that variables here. That's why we are enabled to add the this header file. Okay. So this code is for what? Full drive mode, full stepping mode. So once we'll do the debug operation, we'll debug it and I will show on the port also. ASM we are done. C. I need the port 2. Port 2. And also I observe on the logic analyzer on the port 2 data. T2. Enter, close it, and just run it. See. So steps I have created on that, and data is going as per that, means 0, 3, 0, C, 6, C, and the 9. Means I am operating the stepper motor with the full drive mode, full stepping mode. That is P2 3 value, then 6 value, C value 09. So like this waveform I'm getting means that stepper motor start rotating with the that angle. The code is very easy, and this is for the delay program only. So I have saved that file also for this stepper motor. If you see here, what pins are required and what drivers are required, all the things are specified here. Now, to operate, as I said, that it operates the full stepping and the half stepping. Full stepping means what? Rotation of stepper with the 3.6 degree for each rotation. Okay, so for it requires the 100 steps to rotate complete one rotor. Means perform the one revolution, it requires the 100 steps in case of full stepping 3.6 degree rotation. Now this is shown for the half stepping, that is 1.8 degree rotation of the rotor. And so it requires the 200 steps to complete the one revolution of the 360 degree. So as I'm simulated this, the data is sent on the port, at port 2, and through the driver, that voltage conversion takes place by using EVLN 2003. So that data is coming on the stepper motor poles, and as per that, internally this rotor going to be rotates with the 1.8 degree only. Yeah? So I can change this data angle by selecting appropriate data on the these pins. So next it is shown for the 8 steps rotation with the 45 degree. See, so it's faster one. So in the 8 steps, one revolution is going to be completed. Meaning is that. So what is exactly stepper motor? We have discussed it is a unipolar, bipolar, two types are there. And as discussed, it has the 4 poles, that is A, B, C, D. By sending this appropriately, I can rotate. But internally on the rotor, we have the number of teeths. And by finding the teeths in the number of poles, we can find the angle of the conversion. This is for the unipolar case, this motor. And the step bipolar, this is there. So this is internal construction of the stepper motor. It has the rotor with number of teeth on that. Okay, and it is the rotor stator winding is there. It has also poles on that, pole windings, we can say. So more clearly, it is shown for that only. When the A pole is coming with the same S, it repels and it will go to the this moment, which 45 degree rotation will be there. Okay, so like this. When I'm sending the data on appropriately, that will be start rotating the internally rotor. It is shown here. You can see that rotor has number of teeth like this. And this is my pole winding 1 A B C D. So which pole I'm activating? As per that, rotor starts rotating. Fourth pole activated, then 1, then 2, then 3, like this. And so it has 3 operating modes: wave drive mode, full drive, and half drive. So we have seen for the full drive mode. This is for the wave drive mode data values. This data can be sent, then it operate in the wave drive. Then full drive, C, we're taking the reverse way, 3, 6, C, 9. Okay. And half drive, it has 8 values for that. I think we have done the solution of this, and we have done with the chapter 4. So chapter 4 is completely finished. 5 or 4 interfacings we have seen that. LCD, 4x4 matrix, ADC, DAC, and so 5 we have seen that. So 5 interfacing with 8051, that finished the chapter number 4. Okay, thank you.